All right. Welcome, everyone. I'm Nicolas Chopin. I'm working at the Answer, and I'm one of the co-organizers of this webinar on Bayesian machine learning, Bayesian statistics. This is also organized with David Rod, who is the host of this meeting, and a few other people from Criteo, who is a French tech company who is supporting this webinar. So this is the very first instance of this seminar. If you have any advice, recommendation, request about how it goes, we would be more than welcome to hear from you. Otherwise, I'm going soon to give the floor, so to speak, the virtual floor to Christian. So Christian Robert does not really need any introduction, I guess. He's a very good friend of mine and my former PhD advisor, but also a very prominent Bayesian statistician and very prominent statistician. He wrote several very important books on Bayesian statistics. He's the only guy I know who has one of his books translated in Japanese and maybe other languages as well. So show you how popular his books and how important they are. Of course, he has many papers, many foundational papers in Bayesian statistics, Bayesian computation, MCMC, the principle of Bayesian inference. In the last few years, Christian was really the leader, essentially, of the movement behind the ABC, which is a set of techniques to deal with models where you cannot compute the likelihood, etc., etc. I'm sure I forget a lot of very positive things to say about Christian, but again, you all know him already, I'm pretty sure. So without further ado, I let Christian start his talk. And just a quick reminder before I let him do that. As I said to who's already present a few minutes ago, if you have a question, you just raise your hand. There's a little hand icon, click on it, and I will check when this happens. Oh, there's already one hand raised. So let me just finish before you ask your question. When you ask a question, you can either try to speak. Be careful first to unmute your microphone, or you can type your question in the chat, okay?
Actually, just do a chat, actually. They would need to be explicitly enabled. Like, we never know, someone could come in and say, like, Fisher's a good bloke or something like that. So you need to be careful.
All right, so the question, all right, so
yeah.
Let me correct. So if you have a question, you raise your hand and then you type it in the chat, and I will interrupt Christian and let him know that there's a question. And as I said, also, Christian might anyway from time to time stop and ask if you guys have questions. All right, so someone was raising his hand or her hand already. Was it? The person who raised his or her hand, could you please type your question?
I think we can go on.
Yeah. All right. So, well, sorry in that case. Christian, I'll let you start. Thanks a lot.
Okay, thank you, Nicolas, for this kind introduction, and thanks for the honor and responsibility to start the series. As progressively we get used to these tools, I hope the flow will get smoother, and hope you will pardon me if it's a bit awkward at the beginning. So this is more of an introduction talk on approximate Bayesian computation, with the last part being dedicated to recent work on ABC Gibbs. But to give a flavor of things we have been doing about the past 10 years on ABC, and the appeal of this technique in challenging problems where more standard Bayesian computational tools cannot handle it. Okay, so I mean, first the view on my first slide is not the view of my window, unfortunately. I mean, that's additional to the poll, if you can guess where it's taken. So there is a longer talk I gave last year at a joint statistical meeting in Denver, which I called the XKCD of ABC, that you can find online, that is a bit longer, but some of the slides are borrowed from that longer introduction. And further, I would like to thank a lot of courses with whom I've been working on ABC in the past 10 or 15 years, from the biology and genetics department in Montpellier, from the econometrics department in Australia, and from various statistics departments around the world. So here is the outline, which I hope I will manage to cover all the way to the end, to cover ABC Gibbs. But I take the opportunity to mention that there was a book that got published last year by Scott Sisson, Yenan Fan, and Mark Beaumont on ABC methods. That is a handbook, meaning that different chapters are written by different people, but with an attempt at unity and coherence that makes it a very good read for learning about ABC up to the current advances in the field. And a last advertising slide, which is that we have another webinar that we call the One Word Approximate Bayesian Computation Seminar that takes place every other Thursday, and which runs at around 12 UK time. That is hosted by the Department of Statistics at the University of Warwick, and offers talks on the current state of the art on ABC methods. Okay, so let's start with the very basics, namely what we're trying to do, which is that we try to understand something about a parameter through a posterior distribution, and traditionally it is defined through a prior. That is something that we most of the time control or manage, because that's our personal choice, and the likelihood that translates information contained as data, which is something that we don't necessarily control. That is given to us in one way or another. And there are a lot of arguments for using this summary of the information contained in the data that I will not cover here today. And usually this is a complex object. The more complex the parameter, or the likelihood, the more complex the object. So we cannot understand it at once by looking just at this function of the parameter theta. And a standard tool to explore this posterior distribution is to launch simulations producing a sequence of parameter values that can be considered as a sample from the posterior distribution, from which we can learn some aspects of the posterior distribution. And the most effective tool along the years is Markov chain Monte Carlo, that manages to learn a lot from knowing little about this posterior, namely the functional form that I gave in the previous slide. Okay, so that's very efficient. That's really something that changed the operation and perception of Bayesian statistics in the past 3 decades, because again, it's something that can be almost automatically implemented. There are, however, difficulties in using MCMC and being unable to call for some of the most automated tools like bugs or STAN, which is that this quantity needs to be available in a numerical format. That is, if I give the machine a value of theta and the value of the observable x-ops, I need to be able to compute in a reasonable time this product. And again, pi is really the issue, but the likelihood may be the culprit for this impossibility. So there are solutions to go around the problem. One of the solutions that came from the early days of MCMC, or even earlier if you wish, is demarginalization, which is that you introduce auxiliary or latent variables to make this quantity the marginal or the integral of something that is more manageable, although living in a larger dimensional space. And I mean, the three solutions that are listed at the bottom of the slides are one way or another way to handle this trick. And when it's feasible, it's more costly, and I mean, it's less precise in the sense that you may require more simulations, but in the end, you're able to produce a picture of the posterior. Okay. But it's not always possible, and so let me go through some toy examples that are still representative of the difficulties. And one early example is one that came in a paper by Arnold Frigesti and courses, including Harvard Roy, where it's a sort of mixture in the sense that it's a weighted sum of two densities. But unfortunately, if you wait, the sum is depending on the current value of x. And so this distribution, due to this additional varying weight, is no longer a standard mixture, and it's missing the normalizing constant. Although it looks like a mixture, but the weights are between 0 and 1, especially because it depends on x. You cannot write directly the normalizing constant, especially if some of the quantities in the mixture are more complicated. Another example that may become a nuisance if the dimension of the space is large enough is the truncated normal distribution on some subspace of R to the K, a subspace A that may be of a complex structure itself, that may be defined by a large number of constraints, like inequalities. And to be able to work with this target when A is complex makes for a difficult life, and in particular, you cannot again find the normalizing constant. A third example that is toyish, but very useful to explain some of the features of ABC is this one where when you observe a normal sample, you suddenly decide, for whatever reason, to replace the sample mean as a sample variance with the sample median and the sample median average deviations as a MAD statistic. And although that's a robust substitute to the sufficient statistic, it becomes an object that is not tractable in the sense that you cannot write down the posterior and you need to approximate it. But the remark is that if I give you the model and the value of the parameters, it's easy to produce realizations of this pair mu hat and sigma hat. So it is a generative model in the sense that the forward problem is easily tractable. Then moving to more advanced problems, all kinds of exponential random graphs are difficult to manage objects from the fact that they are intractable thanks to the missing normalizing constant. So if the distribution of the data is from one of these random graphs or spatial Markov models, then the likelihood is not something you can manage, even though there may again exist ways to produce realizations from such graphs. And I will not go into more realistic applications because this would take too much time. But of course, there are motivating objects that started the run for substitutes to MCMC, and one of these models is the population genetic models linked to Kingman's coalescent, where different populations are linked to an ancestor from which they evolved in a very random manner. And the description of the model is very simple. When you start from the common ancestor and diffused geographically to the populations. But going from the current populations or observed populations back to the ancestor makes for a very delicate inverse problem that MCMC or important sampling are not able to tackle. And then other examples in other other domains appear gradually along the years from the alpha stable distributions to all kinds of models related to, for instance, astrostatistics or cosmos statistics that you can find references through these pointers. Okay. Okay, so this is just to try to motivate you. Again, the examples I gave are very toyish and are absolutely not representative of the complexities that can be tackled by ABC. So ABC is an acronym for approximate Bayesian computation. It means that we will not choose the correct likelihood because it is not available, and it's not a pseudo marginal approach, so we cannot approximate it in a trustworthy manner, although there are links with pseudo marginal MCMC. It is a Bayesian approach in that we are really building on a prior. We are constructing an object in the parameter space that is a form of posterior, and it is computational in the sense that almost irremediably we do produce a sample from this pseudo posterior and use it as in other Markov chain Monte Carlo, or at least Monte Carlo methods. And so it creates a sort of conundrum from a philosophical perspective in that this is not truly Bayesian, but that's a kind of poor person Bayesian approach in that we cannot do better, and we replace the ideal of the perfect data, the perfect information contained in the data with a rough version of the data in the sense that it gets transformed into clumps represented by balls. The likelihood is replaced by a non-parametric approximation, and there's a perfect information represented by sufficient statistics, whatever that means, are replaced by non-sufficient statistics. And of course, on top of this cake comes the layer of Monte Carlo error, as usual, but in a worse way in a sense. Okay, so the idea dates back to earlier representation of Bayesian inference to try to explain the meaning of Bayesian inference. It's based on a very basic property, which is that if you start from a prior distribution pi of theta and a true model f of x parameterized by theta, if you produce pairs of parameters and pseudo observations, so theta prime and z conditional on theta prime, so you simulate from the predictive distribution in Bayesian terms, the loop that exists when this simulation reproduces exactly the data, so when z is equal to x ops, is a simulation from the posterior distribution. That is, a theta prime that allows for exiting the loop is a realization from the posterior distribution. And the explanation is trivial. It is a stopping rule that is obtained with a probability of f of y, which should be x ops, sorry, f of x ops given theta. And so you change the distribution from pi to pi times f of x ops given theta, and that's your posterior. Now, of course, that's a very nice explanation in that you use a prior to reproduce what happened in reality. So it's the prior is just a way to explore the parameter space to spot values of the parameters that are compatible in this ideal sense with your data. But it's not practical because in any but very toyish problems, to obtain a new relation of x ops is really impossible. That is, the probability is either exactly 0 if we are in a continuous space for the observations, or it is practically 0 for all computational purposes. And so you may guess the next step is to get approximate and to allow for variability away from x ops, which has, I mean, there is nothing wrong with that in the sense that, I mean, the data is random, and so, I mean, the same parameter may produce different values of the observation, obviously. And so instead of accepting when z is equal to x ops, ABC will accept when z is close enough to x ops. So rho is a distance that, again, ideally has no importance because we would like to take this epsilon to be 0, but in practice, we have to move away from 0, and then rho becomes important in the quality of the approximation. So the new outcome from this inference is not posterior in the classical sense, but it is a posterior in the sense of observing this quantity. Of course, this is a bit cheating because we observe x ops, but let's say that we replace x ops with this event. We know that this event occurred. What is the new information on theta starting from the prior? And so it's a new posterior with this ball-like information on the observation. And of course, the ideal is to take epsilon to be small for precision, but large enough for this probability to happen often enough so that we don't run the loop for forever. So describing the ABC algorithm in a code-like manner, you get something that is very simple. You keep repeating simulations of prior and from the sampling density, which means simulating from the predictive until you can accept realizations. And then you add this realization to the sample. So there is a new notation in this slide, which is eta. Eta denotes a statistic that is a transform of the data that is not bijective, but furthermore not necessarily sufficient, or almost always insufficient. And in this branch, it's called summary statistic, which is a redundant, obviously. So that means that because when the data may be of a very large size, instead of comparing the raw data, we first summarize it into a statistic, and we do compare the statistics that are obviously chosen to be as relevant as possible to infer about theta, and compare those. So it's a dimension reduction or sparsity step to make things better in the end, even though we throw away some information from the data. Okay. And so, I mean, this is just, you can take it as a picture, not as a code, but this is to tell you how precise you can make it. For my robust toy example, I simulated points on parameters mu and sigma from the prior, and the blue dots are those I accepted after choosing an epsilon. And maybe the only line that matters is how I chose the epsilon in this toy example, where I took a quantile on the distances I simulated from the prior predictive. And for instance, I took the 10% quantile. So this last line here is just meaning that I chose epsilon not from a statistical perspective, but just from my simulation. Okay, so that's my example. Can I erase it? Probably I can. All right. So the inference we derive is once again exact, but for the wrong posterior. So it's like answering the right question for the right answer to the wrong question. Is that we do produce an auxiliary variable, that is this pseudo data, from the sampling distribution constrained by this link between Z and X ops, which is that the distance between those summaries is small enough. And of course, if you can prove that if you push epsilon to 0, you do get an approximation that is no longer a ball but a point, and the point that you condition on eta. So with enough power or enough observations, as we will not go into that direction, but with enough observation, you can push epsilon to 0 and get an inference that is almost as good as an inference on theta. And I mean, the recent literature on the convergence of ABC methods shows that depending on the speed of convergence of this summary statistic to a function of theta, you can pick epsilon that is slightly faster than that speed and get optimal convergence properties for the posterior, the ABC posterior. This is how we would call it. And so, I mean, from a mathematical perspective, there are guarantees that ABC can provide an answer that, with the sample size growing, is almost as good as the answer based on eta of X ops. You can never recover an answer as good as given X ops because the loss is done. I mean, is gone, so we cannot recover it. Now, this question of summaries is quite important, both statistically and computationally. I mean, the first argument is mathematical in that, I mean, reducing the dimension of the data down to the dimension of the parameter is quite important to be more efficient. And this is not restricted to ABC. I mean, there are a lot of arguments in the statistical literature about this, but again, the most recent developments in ABC convergence theory demonstrate that the optimal choice of a summary statistic is one of an estimator of theta with the same dimension as theta, well, that is as good as possible. Increasing dimension will always diminish the efficiency of that convergence. And other arguments linked with that mathematical background are that, I mean, the tolerance that you can construct will depend on one side on your computing abilities, but on the other side, on the other hand, on the dimension of the statistic. And so you only do worse by increasing the number of summary statistics. And of course, a lame argument is also that sometimes you may be unable to get the entire observation, or at least to store the entire observation on a single machine. And so you're kind of forced to use from the start summary statistic. Okay, I mean, these are in a silly example, but just quickly that if you have an MA2 model and suddenly you decide that MA2 is not something you can handle analytically, you could try to compare the observed series. So X ops is, say, the light blue lines with a simulated MA2 series, which is the dark blue line, and try to say, well, they look the same or they don't look the same. But there is a lot of noise in this comparison, and I mean, this doesn't tell you much about theta 1 and theta 2. Instead, you could say, well, I mean, this is a two-dimensional model, and so if I use the autocorrelation or the partial autocorrelation or something of dimension 2 that relate to theta 1 and theta 2, well, I do get this distribution of theta 1 and theta 2 that is for a given value of theta 1 and theta 2. So it's kind of reasonable to assume that you get a lot of information about the true value of theta 1 and theta 2 from this distribution, much more than the row series. And comparing the outcome of an ABC based on the summaries or on the raw data, you can see that for the same number of simulations, picking epsilon as a quantile of the distances, as you grow from 10% to 0.1%, you get a much more concentrated ABC posterior here than you do get here, and for the same computing cost. And of course, the true, I mean, you never get the truth, but you get quicker to a good ABC approximation by using this summary.
Christian?
Of course, sorry?
Christian, sorry to interrupt. I think someone has a question. Maybe it's a good time to make a little break anyway.
Definitely.
So if you have question, please type it in the chat, or also there's a Q&A box that you can use.
Can I just ask for clarification, Christian? You said that the higher the dimension of the summary, it actually gets worse. What's the intuition there? Because I would have thought it would be more faithful with higher dimension.
Yeah, it's, if you think of information, it is always better to increase the dimension of the summary. However, I mean, the higher the dimension, the more viable is the summary. And so there is always a way to bring it down to a smaller dimension and keep the same amount of information, essentially. So the distance, that's not a sure thing in a specific case. That if you give me a 10-dimensional summary, there may be an 11th summary that increases the efficiency and therefore the concentration of the posterior. But by another choice of a summary statistic, I would do better. So that's the spirit in that asymptotically you do have the fastest speed of convergence if your summary is of the right dimension.
Okay.
Christian, we have 2 questions in the Q&A box plus 1 in the chat.
Yeah, unfortunately, I just don't.
I can read them if you want.
Please, because I just don't see them.
Right. So starting from the Q&A, slide 6, shouldn't it be P of x ops given theta for the first term? Slide 6.
I mean, from the very beginning. Is it here?
I don't know. Yes. Someone said yes.
So that's the likelihood. That's f of x ops given theta, if you want, yes.
I guess that person meant for the last term, last factor.
Yeah, we can also write it as, yeah, and it's just another notation, but it's the same thing here, like
Okay.
here as well. And then later, maybe I use another notation. Which is,
another question, how do we sample from F if F is intractable?
Okay, so there are a lot of cases where you know the process that leads to the observation. So if I get to this example, which is very tight, I can produce, if you give me mu and sigma, I can produce billions of mu hats and sigma hats. I think someone has forgotten to mute a microphone here. Yes, mu hat and sigma hat are easily produced, but I'm gonna try down their joint distribution. Similarly, if I go to the historical starting point for ABC, which is a Kingman's coalescent, describing the evolution from a common ancestor to, say, a population of bees in 3 different countries is easily done by a Poisson process. You follow a tree, and on each branch of the tree you change some values on the genome of the species, and it keeps changing, and you end up with 3 different genomes that are easily produced. But now, if I have the 3 genomes at the current time to integrate over all these changes, of which there is a random number, and all the possible random events that occurred along that tree, makes for an impossible integration. And so, I mean, the sheer size of producing the observed likelihood is just not feasible. Alpha stable distributions are another example for which it is possible to simulate radiation from alpha stable distributions, but they are defined through their characteristic function, and so there is no closed form for the likelihood.
Christian, we have one third question from Barkop in the chat. I don't know if you see at least the question in the chat.
No.
Okay, let me read it. But is ABC works for the variance parameter for noise in the MA2 process or any regression model, for example, where there can be more error terms, each having a variance parameter which can be unidentifiable? Do you want me to read that again? Or?
No, that's yeah, in principle it does. That if you have, even if you have a non-identifiable model, assuming you have a proper prior, I mean, that's, I didn't mention it, but obviously that's a restriction at this stage. I mean, ABC doesn't work if pi is not a proper prior, but if you have a proper prior on all the parameters, that makes them identifiable in that sense that you can simulate from them and therefore return an ABC outcome. So obviously if you complexify the MA2 model to the point that it's not tractable otherwise, on principle you can run ABC. I mean, I will come back to the dimension of the parameter later. Okay. Nicolas, is okay?
Oh, sorry, I'm muted.
Yeah, you were off. Sorry, you were off.
Yeah. I was saying there's also a question by Julien, but Julien, you have to type your question in the chat. And yeah, maybe it's best. Should we move on for the moment? I'm sorry, and so that we can.
Sorry, I didn't have any question. That was probably a mistake from me.
Okay, so please mute your microphone from now on. I will do the same, and maybe we can go on and go back to a question and answer session in a.
No, but sure, yeah, but I mean, please stop me. Like, otherwise, I will forget to ask for question again. Yeah, so this summary aspect is somewhat vexing in that there is no definite answer, because I mentioned this optimality of summaries of the same dimension as the parameter, but of course some summaries are optimal, some are worse, and so if we could do without the summaries, we would escape this calibration problem. That is, in a sense, akin to designing good empirical likelihood approximations. If you run empirical likelihood as your method of inference, that is, you define your model through constraints that characterize your parameter, but this definition is quite subjective. So there exist some solutions that try to avoid the selection of summaries, but they are, I mean, not ideally suited to all problems. So I mentioned here one solution that we tried with courses 2 years ago, that is using Wasserstein distances to compare samples, in the sense that the points themselves are not interesting. They are interesting only by representing a certain hidden distribution. And so using distances between distributions could be a way to overcome the choice of the summary statistics. And this is feasible in small dimensions for the observations. It gets more costly as the dimension of the observation increases. And in that sense, there is a link with GANs, generative adversarial networks, in that we just replace the data with pseudo data, and we try to see how they confuse one another. So there are solutions, but not universal, I would say. So if the summaries are not forced upon you, which again may happen, there are ways to try to select the summary statistics and curl them when there's a large number of them. Some are somewhat naively statistic, like running a variable selection approach. Some are trying to take advantage of decision theoretic principles, as the red paper by Profunded and Dennis Prangle, where they showed that from this decision theoretic perspective, actually the best summary statistics is the expectation of theta given x, which is not available because otherwise we would not run the approach, but that can be approximated in a recursive manner. And then there are links with other methods, so for instance, in econometrics, where auxiliary models are only there to produce summary statistics. So this is a solution that has been running for quite a few years now. I will mention that later in more detail. So we can use random forest to build estimators and incidentally select summaries. And then there are more advanced ways to try to eliminate summaries that are superfluous. So I mean, there are a lot of papers that go this lane of finding summary statistics. Okay, in the interest of time, because I think I'm running late, I will not go into more details into the Fernhead and Prangle red paper, and you can find it also described in the book. Similarly, I will not re-describe what a random forest is, but running ABC random forest is possible. Yes?
Sorry to interrupt, since you're starting a new part. There were two questions I didn't read last time. Maybe you want to answer them.
Yes.
Is there any data-driven way to choose the summary statistics? Data-driven way to choose the summary stats?
Well, it depends what you mean by data-driven. There are a lot of methods that rely on the simulations from the predictives. I mean, so the bulk of the computation in ABC is producing a large enough sample from the predictive, or for something between the predictive and the posterior, to learn indirectly about the likelihood. And so all summary design methods are based on that reference table or predictive sample. Now, more advanced method will start from this learning base and iterate by trying to get closer to the posterior. So there will be a sequence of ABC steps or important steps or other or indirect inference steps or synthetic likelihood steps, where each time you get a sample that is no longer from the predictive, but from something that is in between. So in that sense, yeah, you learn from the data to build a better proposal. And of course, that includes taking in and taking out summary statistics.
Christian, next question. How does ABC compare to a regular MCMC method? like Metropolis, if you use a likelihood on MCMC and the sufficient stat on the likelihood on V4, I'm not sure I understand.
No, so I mean, that's a very good question. That there is very little reason to use ABC if instead you can run MCMC in a reasonable time. I mean, the only appeal of using ABC in such setups would be that the gain in computing time would be enormous and meaningful for the end problem. Otherwise, it's an approximate method. So you create more noise for no statistical purpose. I mean, the only advantage is because you can produce something quickly. So it's really a dirty version of MCMC. But that's a good question because that's I should have pointed it out. Yeah.
Maybe last question before we move on. How do we choose proper priors, or do we know we do have worse prior information for the parameters?
Okay, so the question of the prior. Actually, I could rephrase the question in a blunter way, which is that I mean, why do we simulate from the prior when we are interested in the posterior, especially if the prior is very vague, and of course the limiting case being improper, where you cannot simulate from it, and that's quite reasonable to object to this choice. I mean, a slightly more advanced version of ABC is not simulating from the prior, but from any proposal and correcting in the simulation for this change. And so maybe if I have time, I will flip through some of this solution, but you have an important sampling version of ABC. You have an MCMC version of ABC, you have a population Monte Carlo version, and so on. So you can get away from simulating from prior, which is, again, statistically a terrible idea. So yes.
All right, I think it's time to move on. So maybe we leave other question for the end of this session. So if you have any extra question, please put them in the Q&A box, and I will read them in turn to Christian. Thank you, Christian. You can proceed.
Okay, so just one last word about random forest, because this was not the original point of the talk, but I mean, random forest are interesting ways to handle summaries, in that as input they can take an almost arbitrary number of summary statistics. And so if computing those summary statistics is not the costly part in the analysis, you can input a lot of predictors, and random forests have a very thick skin in that they can ignore the useless components in this vector of predictors. And they are very fast to sift through the predictors and return very few summary statistics that predict either a class if you're interested in a model, or a parameter value if you are directly interested in parameter. I mean, they are not the end of the game Bayesian inference-wise, but they have a very good ability to manage summaries and selecting those summaries. The tolerance I gave this example at the beginning, that again the tolerance is not something that is intrinsically statistical, is not linked with the original statistical problem, but as soon as you start looking at the convergence of ABC posteriors, you can spot that the tolerance is very directly connected with the speed of convergence of the summary statistic. And so there is a natural threshold linked with the sample size that should be used, even though it's a theoretical construct that in practical situation is not achievable. But there is a form of natural threshold that if you can run experiments like Monte Carlo experiments on the ABC construct, will appear that as a natural choice of epsilon. So there is a very empirical version of this theoretical convergence. Okay, because I assume we have about 10 minutes left. Is this correct?
Yes, 10 minutes, okay.
Or 5 if you prefer.
Take your time because we got interrupted several times.
It's not interruptive. It's nice to have questions. So it's good.
Yeah, my bad. Sorry.
So I mean, let me try to. Oh, I can't do that anymore. There is a paper, a chapter in the book I mentioned by Nunez and Prangle that covers, I mean, the computational aspect of ABC by going through a different software that I strongly recommend. And well, these were the versions of ABC I will not cover. So let me go through quickly. So these two steps: a big data, big parameter. Big data is really an issue in that most of the time when you run ABC, it is linear in the sample size or worse. And so given that you have to produce a lot of samples or pseudo samples that you will compare with your observations, this itself may become a very costly procedure, and ABC may fail to operate simply because it's impossible to reproduce data in enough copies to make it of any use, of any precision. And so there are more advanced version of ABC that appeared recently, where people try to first build a reasonable approximation to the likelihood and then simulate from this approximation rather than from the true likelihood. So they use a small sample to learn the likelihood and then produce a larger sample based on the approximation. There was a talk on the one-word ABC seminar 3 weeks ago by Dennis Prangle, which was based on that idea using rational encoders and things like that to replace the model with a cheaper substitute. And other solutions using copulars, synthetic likelihood, have been also proposed to move faster to a prediction of the data. To the point that I mean, you get solutions that are big O of 1 rather than big O of n in the sample size. And these remarks were based on scalable MCMC, where I mean, you could try, if you had the power, to split your data on parallel processors or computers to run ABC on different threads and at the end aggregate those. And so this is borrowing from literature on MCMC with no strong addenda at the ABC level. And so if I may take another 5 minutes of your time, let me reach the selling point of the talk, which was ABC Gibbs, which is a big parameter issue. ABC is not very good at bearing large parameter spaces because if you can shrink the sample to the dimension of the parameter, you cannot shrink any further than the dimension of the parameter. So there is a curse for dimensionality more in the parameter space than in the observation space. And so, I mean, some solutions are removing some of the parameters by turning them into nuisance parameters, in the sense that the distance will only cater a sub parameter, so a subvector of the parameter. Another way is to try to return to the sources of MCMC and call this a magic dimension reduction that is a Gibbs sampler, and run the ABC version that is ABC Gibbs. That is, if you have a model that is with many parameters, and that is, for instance, hierarchical, as in this toy model of an hierarchical MA2 model, where different series are linked with parameters mu1, sigma1, mu2, sigma2, and so on, and they are all linked with hyper prior driven by alpha and sigma. Given this separation brought in this graph by the hierarchy, namely that x1, x2, xn are independent from one another, given, for instance, the top alpha and the bottom sigma, it is possible to reduce the dimension when considering the summary statistic. And rather than trying to implement a vanilla ABC that will crash almost irremediably if the dimension is large, even though you have a lot of simulation. And this picture is just meant to mean that the ABC sample is a neat fit to this curve, but unfortunately the curve is a prior and not the posterior. Instead, try to take advantage of partial independence properties to run an ABC that reduces the size of the summary statistic. That is, when looking at this picture of the ABC code, ABC Gibbs code, for each component of the vector theta, you run a different ABC approximation that relates to a different tolerance and a different summary statistic. And this summary statistic is essentially, to make it simple, a local estimate of theta j based on the data, of course, but also on the other parameters. So you condition on the parameters. You have a conditional model that is of small dimension, I mean, ideally of dimension 1. And in that case, the summary statistics may be of dimension 1, and therefore the epsilon may be very, very small. And if you keep cycling through all the thetas, you will produce an ABC approximation to the posterior, but that has gone only through one dimension at a time. So of course, it's still big O of n in the parameter space dimension, but at each level, the ABC will be precise enough in the sense that it will be in small dimension. And of course, there is an immediate caveat that appears with this proposal, which is statistical. It means that for each parameter, we are running inference based on different data because it's based on a different statistic. And therefore, even if we could push epsilon to 0 at each step of the ABC, we will return with a posterior that doesn't exist, in the sense that we have different conditionals that do not belong to a common joint posterior. And so for that reason, that causes the same difficulty as with regular Gibbs, namely that if you run a Gibbs sampler where the conditionals are not taken from a common joint, I mean, the Gibbs sampler may well diverge. There is not Markov chain theory guarantee in that case, or you have to prove it case by case that there does exist a joint that relates to this disconnected conditional. So, I mean, this is a debate where we have to demonstrate that it works. And I mean, this paper with Grégoire and my other courses does consider this too. But I mean, there is a dimension reduction that makes it work definitely better. And there are pictures to try to give an idea about that. Okay, so I've reached my last slide, which is the time where we can ask questions, but let me leave that open, that we are interested in candidates for two ABC or approximate Bayes related postdocs, either in Paris or Saclay or Montpellier. So if you're interested, please contact me.
Thanks a lot, Christian. Let me clap for everybody. If you want to show your appreciation, just write something in the chat. Guys, if you have questions, the best thing to do is to type it in the Q&A box. And I will read the questions in order to Christian. All right.
Oh, I can read it now.
Oh, great. So it's just at the bottom of the Q&A, and there are two questions at the moment.
Yeah, so I first enter the question from Rohit that when there is a large number of summary statistics, you fit statistics that are easier to compute, or you start with a large bunch and you let the random forest choose. I think there is no hard answer to this question. My proposal would be indeed to follow the random forest path. Once again, because it's fast, assuming that the statistics are easy to fit. If you are in the opposite situation where some statistics are very costly while some are cheap, I would follow the finite and triangle track, where I would construct with those cheap statistics a first approximation to the posterior, and then simulate from this posterior, because in that case, I would have a more concentrated sample of theta's, therefore need less simulations of pseudo observations. And so I would try to gain in that direction. So in that sense, it's a very good question, where in that you have the two proposals that are good solutions depending on the situation. So it's just a balance between how costly it is to produce some of the summary statistics, which on some tree structures may become quite costly. Okay, and another question from an anonymous attendee. If the number of observations is large, too expensive to simulate, can you simulate with a mini-match of observations? And so with the simulated sample of the parameters, in that case, would be from a tempered version. Yeah, exactly. If I had times to go through my slides, this was the proposal we made. Once again, it's a sort of finite and triangle track, if you wish, in the sense that you can proceed sequentially through your data batches, and each time produce a small sample of theta's and with associated summary statistics, and each time grow towards the entire ABC posterior. And so depending on the cases, that's a fairly reasonable way to proceed. If instead you have parallel processing that is available, or that is kind of forced upon you because the data cannot be stored in the same location, then you can run all ABC with mini batches in parallel, and then aggregate them by one tool or another that is, for instance, borrowed from ABC. Another question is the connection between ABC and streaming stochastic rational Bayes. I have no idea. I mean, regular rational Bayes is making the best of a simplified version of your model that, in my vision, cuts some branches in the dependence graph. So that is able to return a pseudo posterior or a weaker posterior in a reasonable time, or sometimes much faster. And so this, if you want to proceed further, could be used to run simulations of theta's and pseudo observations and proceed to the next step. Yeah. Another question is comparison between ABC and deep learning. I don't think I have any deep answer to provide. To me, they are very different things. I can hardly see a link at this stage. Accepting PhD students, well, we can talk about that outside this forum, but yes, why not? Bayesian interpretation of the random forest algorithm. That's a very good question. Actually, random forests do produce samples in the parameter space, but my understanding of those samples is that they are not random in the same spirit as a posterior sample is. So they are not genuinely Bayesian in that respect. And the last question, I'm sorry, I'm speeding up a little bit, but the last question is the conditions for ABC Gibbs to converge are, on the one hand, very restrictive in that you must get some form of uniform ergodicity at one level of the hierarchy. There is a sort of lumpability principle here that makes one level good enough for all the levels. So theoretically, it's somehow hard to prove that there is ergodicity and convergence to something that is close to the true target. Surprisingly, convergence, I mean, we have not been able to produce anything that is not extremely exotic and that doesn't converge. So, I mean, there's convergence to something that is not the true posterior, that may be using some parts of the data twice and some other parts never. I mean, it's a sort of complex object that may be too concentrated on one direction and not enough in another. But in every attempt we made to use this Gibbs version, it worked. And if Ed is listening, I must mention that we didn't try cases where the prior is improper. So we didn't try the great examples of Gibbs for kids that he and George used in their 92 paper. So that makes me think that we should try that as well. But apart from this question of improperness, where regular ABC works for improper pairs, you just have to run it differently. I don't know if ABC Gibbs would fall into the difficulty connected with improperness. But that's yeah, I've been rushing through the last part, but that's a very good question, of course. I would say in practice, my belief and experience is that this question of compatibility is very frustrating for me on the theoretical part, but on the practical side, I didn't encounter anything frightening in that respect. Even though we are currently working on finding versions that have a guaranteed joint distribution by using auxiliary variables. So that's work in progress.
Thanks a lot, Christian. There's one more question, but I will answer it myself. Yes, the recording of the talk will be available soon. All right, so I guess there are no more questions. Anyone? So I'd like to thank first the attendees. That was very nice. You showed in such large numbers.
Attendees, yeah.
If you have any, since this is the first time we do this, if you have any feedback, any recommendation, feel free to send us an email. I'd like to thank Criteo again, the company who is supporting these webinars, and my colleagues at Criteo who are co-organizing this. And last but not least, of course, let me thank again Christian for this very interesting talk on ABC. Thanks a lot, Christian.
Thanks for attending. Thanks.